non-negative measurable function is the limit of an increasing sequence of simple functions. And therefore, we now define integral f d mu of x as the supremum. So this is the definition of integral phi d mu of x, where 0 less than equal to phi less than equal to f, phi simple. So this is the definition of the integral of a non-negative measurable function. It always exists, whether it may be finite, it may be infinite, that we don't know, but the definition is clear. Okay, so every non-negative measurable function is integral. Integral is defined. Integrable is a different word. Okay. Finally, if E is contained in X, then we define integral over of f d mu over E as integral over X f into chi of E. Cut off everything else. Outside E you cut it off, make it 0. Inside E it is same as f. So it is enough to study integral over x, don't have to worry about integral over. So let us see what we mean by the integral with respect to some measures which we have seen. So let us take n, x equals n, s is the power set, and mu equals the bounding measure. Since every set is measurable, every function is also a measurable function. There is nothing to check. So what is the function from x to r? That means it is a sequence given by f of n. Okay? X is 1, 2, 3, etc. What is the function? It is a real number. For each n you give a real number f of n. So really you are talking of a sequence here. So it is a sequence f of n. So you want to know what is the integral of f. So let us take a simple function. We take a simple function, that means what? Let us say chi. So let us take chi of just some 1n, a single. So what is its integral? It is equal to 1, the coefficient, into the measure of this set, which is just 1. So suppose I had alpha here, then it will be alpha times this, so it is alpha. So suppose I have a function phi, which is alpha I for 1 less than equal to I less than equal to n and 0 afterwards. This is equal to phi is equal to sigma alpha I chi of I equals 1 to n. So what is the integral of phi d mu? Equals sigma alpha I, measure of the singleton I, which is sigma alpha. Okay. Now if you are given an arbitrary function, maybe a sequence of real numbers, f is nothing but the supremum of phi n over n, where phi n equals phi n of I equals f of I if 1 less than I less than n and 0 if I is 2. So integral f dq by definition is the supremum of integral phi dv, p and dv, and that is nothing but sigma n equals 1 by. So integration of a non-negative function with respect to the Haugen measure is nothing but summation of the series. That's all. What is the other measure we saw? Dirac measure. So let us see what is the Dirac measure. So x is any set, x naught belongs to x, s is the power set of x, and mu is the Dirac measure at x naught. That means mu of E equals 1 if x naught is in E, 0 if x naught is not. Phi to be any simple function alpha I chi of t. Then integral phi d mu is sigma alpha I times mu of E. Suppose x naught does not belong to EI for all that. Then all of these are 0. So this will become 0. But it is also equal to phi of x naught. Because x naught is not any of the EI, so chi of EI is 0. So phi of x naught is 0. Suppose x naught belongs to some EI, it will belong exactly to 1 because I said you can always write the EI as disjoint. So it belongs to EI naught and not to any of the others. So then what is phi of x naught? Equal to alpha I naught into 1, others will all be 0. Now what about the integral of phi d mu? Here only EI naught will have measure 1, all the EI's others will have measure 0, and therefore this will also be alpha I naught, which is phi of x naught. So the integration of any simple function with respect to the Dirac measure is nothing but the evaluation of that function at x naught. Now what is the definition of the integral? It is supremum of integral 0 less than phi less than f, phi simple. So integral of any function f non-negative will just become f of x because it is the supremum of phi of x naught where phi is less than equal to f, and that will be just f of x naught. So integration with respect to Dirac measure is just evaluation at that point. Find the integral only for non-negative functions, but I want to define it for arbitrary measurable functions. So you say that a function f is integrable on x if integral over x mod f dq is finite. Mod f is a non-negative function, so the integral is defined. It may be a finite or infinite number. Now if it is strictly finite, then we say the function is integrable over x. This is just like saying absolutely convertible. Done. And any function f can be written as f plus minus f minus. In fact, another way of writing f plus is f plus mod f plus f divided by 2, and f minus is mod f minus f. So you have integral of f plus integral f minus d mu is fine. Now we can show that integration is a linear operation. Okay, that one has to prove. So that means integral f plus integral f minus is fine. So each of them is fine. So now I can define integral f d mu over x as integral f plus d mu over x minus integral f minus d mu. Because now I can subtract. Everything is finite, so subtraction is a legal operation. This is why we need to go to integrable functions. So in series you say every absolutely convergent series is convergent. That's what the same thing is. If it's integrable, then the integral is well defined and it is finite. So this is how you define the integral for an arbitrary function, provided it's an integrable function. This is the name, that's why we say it is integrable. That means I can define its integral. So this definition there, why did I say it is integrable? Because if it is integrable, then I can define the integral of this function. So an integrable function, you define this. From here the complex is just one step. Complex function. So that means f is from x to c. So then you write f of x equals ux plus ivx, where u and v are real functions. So these are the real and imaginary parts of that function. So you say that f is measurable if u and v are measurable. F is integrable, same definition, integral mod f is fine. But what is mod f? It is square root of u square plus v square by 2. Okay, so this will mean that integral mod u is finite, integral mod v is also finite. So u and v are both integrable functions, so their integrals can be defined. And so in a natural fashion, I define integral f d mu. So this way for all complex measurable functions, define the integral. So the condition is that the function should be integrable, which means mod f should have finite integral, and mod f we have the definition because for any non-negative function we have defined. So this is how integration is defined over any integral. And then there are three very nice limit theorems which have plenty of applications, which unfortunately I have written down about 20 exercises, but I don't have time to do any of them. So first one is called the monotone convergence theorem. So if 0 less than equal to f1 less than equal to f2 infinity, and Fn converges to F pointwise. So you have a sequence of monotonically increasing non-negative functions. That means for each x, 0 less than f1x less than f2x less than f3x etc. and fnx converges to f of x. Then limit n tending to infinity integral over x fn dq equals infinity. Very easy theorem to apply, very simple hypothesis. Second is, if Fn is non-negative for all n and Fn converges to F pointwise, then integral of f dv of x is less than or equal to limit integral f dv. This is called Fabre's lemma. Inequality can be strict. Suppose I take x equals n, s is the power set, mu is the counting measure. Then let us take fn of x. Fn equals characteristic function of n plus 1, n plus 2, etc. So this function will be 1 if n is bigger than or equal to n and 0 before. So what is integral fn dq? It is plus infinity. Because it is 1 plus 1 plus 1 plus 1 infinite number of times, it is plus infinity. So limit fn dmu is also plus infinity. But what does fn converge to? For every m, if n is sufficiently large, m will be less than n. So fn of m will be 0. So the sequence is terminally 0. So fn converges to 0. So here you will have 0, here you will have infinity. So you can have strict inequality. So this is the best you can do. So here we are assuming nothing. We are just assuming pointwise convergence and non-negativity. And then we get an inequality with some relationship between the integrals. And of course, the most powerful, almost constantly, is the dominating convergence. This says as if fn converges to f almost everywhere and mod fn is less than or equal to g for all n and integral g is finite. Then integral mod fn minus f dv of x goes to 0 okay, and integral fn dv of x. second is the immediate consequence first. So one last word. In almost every limit process involving integration, somehow or other will make an appearance. Okay. Very powerful theorem, but very simple hypothesis. Fn should converge to F, and all the Fn's must be bounded by an integrable function. And then we can have whatever we want. We say that, so we have pointwise convergence. We have almost everywhere convergence. Well, these two are more or less the same. Then we had convergence in measure. Now we have convergence in mean. What do we say? Fn converges to F in mean, or Fn converges to F in L1. These two are identical words. If integral mod Fn minus F in So, if you have pointwise convergence, and if all of them are bounded by an integrable function, then it implies convergence in the mean. That is the dominant convergence here. So, if you have convergence in the mean, what can you say about other types of convergence? So, if you have pointwise convergence and finite measure, then it converges in measure. If it converges in measure, for the subsequence it converges in pointwise almost everywhere. Okay? So what is now the connection between convergence in mean and the other convergences? Convergence in mean implies convergence in measure. So let us take E epsilon to be the set of all x, such that mod Fn x minus Fx is bigger than or equal to x. Now integral over x mod Fn minus F d mu is bigger than or equal to the integral over a smaller set. So En epsilon mod Fn minus F d mu. But on the set, this is bigger than or equal to epsilon. So this is bigger than or equal to epsilon times, there is nothing inside, there is the function 1, so that will give you the measure of En epsilon. But this goes to 0. It is given. So this has to go to 0. So convergence in mean implies convergence in measure. But convergence in measure means for the subsequence you have convergence almost. So, pointwise convergence implies convergence in measure in finite measure case. Convergence in mean implies convergence in measure. And convergence in measure means for the subsequence you have pointwise convergence. So, these are the interrelationships between the different kinds of convergence. Okay, I am afraid I have to. Okay, it's over. 3 seconds. Thanks.
This section I want to work out some examples and problems. I cannot be moving at the pace at which I was moving in the morning because then I will not be able to cover anything. So I will assume that you are familiar with certain basic concepts, and as and when required I will recall the definition but not spend too much time. But we will work out instead problems based on those concepts. Okay. So in the morning I ended my lecture with one question: whether rational numbers form a dense subset of Rn. We all know rational numbers is dense in R, but Rn, when you change the topology, you have to wonder if this will be the case. What do you think is the answer? The answer is yes. So to show that it is yes, what do you have to show? You have to show every point of real numbers is the limit point. Okay? Or yeah, equivalent. So give yourself next. A, B, or else. Okay? Now you take any basic open set surrounding that. Then all you have to do is find the rational number, where rational number is that here. Here. So if you remember the definition, okay. So to show that some point, I want to show that A is a limit point of rational numbers. Okay. In order to show that, what should I do? Alright, I should just write any open set, in particular just enough to do it only for basic open set. Write any basic open set containing this. Then in that open set, I must find a rational number other than possibly A itself. A itself could be a rational number, doesn't matter. I must find some rational number other than. If I do that, then I will be showing that A, that point is a limit point. So, but basic open set in this containing this will be of this form. Okay? If it is a usual real number system with usual topology, then you will write a picture like that. Okay? But this time we have to draw a picture like this. But anyway, this is some interval. And inside of this, I can always find a C in the open interval. That means other than A, I can find a rational number C which belongs here. Okay? So, let A be here. Now I write something like this. Yeah, basic open set. Open set. Contains A some form. A comma B. 1 or x comma y. Many cases. We can find the rational number or its C. U is either this or this. C not rational numbers. Therefore, Q is rational. This is okay. Now I have some two more questions to reflect the topology of RL. So next, this is the first problem. So find the limit points of the sequence. 1 by n in RL. In R we all know sequence 1 by n converges to 0. What about it in RL? Okay. So again, remember that in oral, the basic open sets or I keep saying this are that nature. Okay? So how does that affect computation of limit points? So what does it mean to say finding limit points? Alright, so you just plot the points on the real line and see how it looks like. Okay? How does it look like? Okay? Now, actually, if you just think of the usual topology on the real line, it converges to origin. Alright? What does that mean? If I take any neighborhood containing the origin in the usual topology, all but finitely many will belong to that open set. Okay? Now, if that is the case, notice that in oral there are, if at all, more number of open sets. Correct? The topology on oral is finer than the topology of R. When such is the case, when you have a sequence which is convergent in the usual topology, in a finer topology, that may or may not be the midpoint, but if it is the midpoint, then that is the only midpoint. Okay? So, now it looks like as you go closer and closer, okay, now origin is the midpoint. Let us guess that 0 is the midpoint and try to prove it. Okay? So, now guess. So here is where drawing picture really helps. So guess. What is the guess? 0 is the only limit point. Okay, let us prove this. First, let us prove that 0 is a limit point. Alright, then it will be easy to show 0 is the only limit point. Okay, so to show 0 is a limit point, all I have to do is I should just write neighborhoods of 0. The basic neighborhoods of 0 which are special to order are of this form 0, epsilon. Epsilon is some positive number. Okay, so I mark that 0, some epsilon. But you see, the moment n is such that n is larger than 1 by epsilon, all the numbers 1 by n are here in this neighborhood. Okay, so contains all the finitely many terms of the sequence of name that code equals 0 in order. So you are going to prove that the sequence converges to origin. Okay? Now, when such is the case, this is the only possible limit point provided your topological space is Hausdorff. Okay, you all know what is Hausdorff, no? So given two distinct points, you can find disjoint neighborhoods surrounding them. And all you need to do is check whether oral has that property. The usual topology or itself has that property. If at all this is a finer topology, so this will also be Hausdorff and we are done. Therefore, 0 is the only. C only. Since orange is Hausdorff. So far, there is no surprise. Same type of thing happened also in R. Why is this space different? So now we will do this following thing. Change the sequence slightly and ask ourselves what is happening. keeping it inside unique points of the sequence 1 by n or set 1 by r 1 minus 1 by n 1 divided by 1 happens. Okay. In this case, what happens? Draw the picture. One is here, 1 by 2, no, then 2 by 3, 3 by 4, what happens? Now this time, with respect to the usual topology, what would be the limit? 1 would be the limit. Okay? And therefore, since the topology here is final, if at all there is a limit point, only 1 could possibly be the limit point. Is 1 the limit point? Is the question. Is 1 the limit point? So you think yes is yes. Limit 1 minus 1 by n is equal to 1 as I goes to infinity. Okay? But in oral, but this is wrong, not true. Why is it not true? Not is it different? We have to write basic open sets containing 1. Of course, if I write the usual open set like that, it would be okay. All alternative meaning would be here. But I am working with oral, there are more special types of open sets. So the open sets I choose are all of this form.